Hello friends, welcome back to my YouTube channel. This is 18th part of my discussion on mass transfer coefficients and under the topic interface mass transfer. Today I will be discussing a numerical example in which you will learn how to find out interfacial concentrations and then how to find out mass transfer flux. So this numerical example is based on my discussion in part number 17. So I hope you must have seen part number 17 and the entire playlist. I'm giving link to the entire playlist of my video lectures on mass transfer coefficients in the description section. So objective is to solve a numerical example where we will be finding out interfacial concentrations, and then by using those interfacial concentrations we will be finding out the mass transfer flux. So let us move ahead. To begin with, first we will look at the numerical statement. So we have solute A is being absorbed from a gaseous mixture of A and B. The equilibrium relationship is given by y star is equal to 0.8 into x star, where x star and y star, they are in equilibrium with each other. At some point in the tower in which this absorption is carried out, at some point in the tower, the mole fraction of A in the bulk gas phase is 0.35 and the mole fraction in the bulk liquid phase is 0.15. The values of individual mass transfer coefficients are given below. So Kx is 1.48 into 10 to the power minus 3 kilomole per meter square per second per mole fraction, and Ky is 1.80 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. So based on this data, we are supposed to find out the following: interfacial concentrations and then the mass transfer flux. So a simple absorption problem is given where you have a gaseous mixture of A and B, and solute A is being absorbed from this mixture into a liquid solvent. The equilibrium relationship is given to us. It is y star is equal to 0.8 into x star, where y star and x star, they are in equilibrium with each other. Then at some point in the tower, the mole fraction of A in the bulk gas phase, it is 0.35, and mole fraction in the bulk liquid phase, it is 0.15. The values of individual mass transfer coefficients, they are given to us. Kx is 1.48 into 10 to the power minus 3 and the unit is kilomole per meter square per second per mole fraction. Ky is 1.80 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. And we are supposed to determine the interfacial concentrations and then the mass transfer flux. So I hope the numerical statement, what is given in the numerical statement, it is clear to you. Let us move ahead. So first of all, we will list the given data. So you have the mass transfer problem is absorption of A from the gas mixture of A and B into a liquid solvent. This is the mass transfer problem. The equilibrium relationship is given to us. It is y star is equal to 0.8 into x star, where y star is composition mole fraction of A in the gas phase, x star is mole fraction of A in the liquid phase, and x star and y star, they are in equilibrium with each other. Then the bulk phase concentrations are given to us. YAG, concentration mole fraction of A in the bulk gas phase, YAG, it is 0.35. Then mole fraction of A in the bulk liquid phase, that is XAL, it is 0.15. Individual mass transfer coefficients, they are given to us. Kx is 1.48 into 10 to the power minus 3 kilomole per meter square per second per mole fraction, and Ky is 1.80 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. What to find? First, we have to get interfacial concentrations. That is, we have to get XAI and YAI, and then we have to get the mass transfer flux, which is NA. So it could be NAG or NAL. So what are NAG and NAL? You please refer my previous video. There I have explained those mass transfer fluxes. So this is the given data. Let us move ahead. Now let us understand what would be the approach to solve this numerically. First, we will be finding out interfacial concentrations, that is XAI and YAI. For that, we will be using equation of the driving force line, which is nothing but YAG minus YAI upon XAL minus XAI, that is equal to minus KX upon KY. And then we will be using the equilibrium relationship, which is nothing but the equation of the equilibrium curve. So the equation of the equilibrium curve, that is equilibrium relationship, is given to us. So we will be using that. And we know that the interfacial concentrations, that is XAI and YAI, they are in equilibrium with each other. So therefore, they should satisfy the equilibrium relationship. Equilibrium relationship is Y star is equal to 0.8 X star. Y star is equal to 0.8 X star. This is the equilibrium relationship. And since XAI and YAI, they are in equilibrium with each other, they will satisfy this equilibrium relationship. So that's why we have this equation, YAI is equal to 0.8 into XAI. So now we have two equations because YAG, XAL, KX, KY, they are known to you. So unknowns are YAI and XAI. And this again, the unknowns are YAI and XAI. So you have two equations, you have two unknowns. You can solve the two equations simultaneously and get the values of XAI and YAI. So thus we have two equations, as I said, in terms of XAI and YAI. You can solve those two equations simultaneously and get the values of XAI and YAI. Then after getting XAI and YAI, next task is to get mass transfer flux. So you can find it either by using this equation, NAG is equal to KY into YAG minus YAI, or you could use NAL is equal to KX into XAI minus XAL. So both the values, that is NAG will be equal to NAL. So you can check that. So in this way, you can find out the mass transfer flux. So I hope the approach is clear to you. If you have any doubts, you please mention that in the comment section. Let us move ahead. Now, let us start the solution. First, let us get interfacial concentrations, that is XAI and YAI. So for that, we are going to use the equation of the driving force line, which is YAG minus YAI upon XAL minus XAI, that is equal to minus KX upon KY. Now YAG is known to us, it is given, it is 0.35. XAL is also given to us, it is 0.15. KX is given to us, it is 1.48 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. KY is given to us, it is 1.80 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. So if I use the given values, it would be 0.35 minus YAI divided by 0.15 minus XAI, that is equal to minus 1.48 into 10 to the power minus 3 divided by 1.80 into 10 to the power minus 3. So that is 0.35 minus YAI upon 0.15 minus XAI, and this ratio is minus 0.822. Let us simplify this further. So that is 0.35 minus YAI is equal to, I will be bringing this term on this side, so it will be 0.35 minus YAI is equal to minus 0.822 into 0.15 minus XAI. Let us simplify it further. So that is 0.35 minus YAI is equal to 0.822 into 0.15 is 0.123. So that is minus 0.123 plus minus 0.822 into minus XAI is plus 0.822 into XAI. That is 0.35. I will bring this term on this side. So this is 0.35 plus 0.123. That is equal to 0.822 XAI. And if I take this term to this side, it will be plus YAI. So that is 0.822 XAI plus YAI is equal to 0.35 0.473. So this is equation 1. Equation 1, it is in terms of xai and yai. Now you have the equilibrium relationship, which is y star is equal to 0.8 x star, and we know that xai and yai, they are in equilibrium with each other, so they will satisfy this equation. So it will be yai is equal to 0.8 into xai, and that is equation 2. So now you have equation 1, equation 2 in terms of xai and yai. Now our job is to solve these two equations simultaneously and get the values of xai and yai. xai and yai. Let us move ahead. So we are getting interfacial concentrations, that is xai and yai. So we have got this equations 0.822 xai plus yai, that is equal to 0.73. It is equation 1. Then we got yai is equal to 0.8 xai. This is equation 2. Now what we will do, we will use equation 2 in equation 1. That is yai in equation 1, we will replace with 0.8 xai. So that is 0.822 xai plus 0.8 xai, that is equal to 0.473. So the addition of this 2 is 1.622 xai, that is equal to 0.473. That is xai is equal to 0.473 divided by 1.622. So that gives us xai as 0.292. Now once you get xai, now you can find out yai by using equation 2. So with equation 2, yai will be equal to 0.8 into 0.292. So that is yai is equal to 0.232. So that gives us the value of yai. So in this way, we have got the interfacial concentrations. Now let us get the mass transfer flux, Na. So for that, Nag is Ky into Yag minus Yai. So Yag is 0.35, Ky is 1.80 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. And Yai we have found out over here, it is 0.232. So therefore Nag is 1.8 into 10 to the power minus 3 into 0.35 minus 0.232. So that gives us Nag as 2.12 into 10 to the power minus 4 kilomole per meter square per second. So in this way, we get the mass transfer flux. We have calculated it by using the equation for the gas phase. Now let us check whether we get the same value by using equation for the liquid phase. We will check that. Let us move ahead. So we got Nag. I will repeat those steps. So Nag is Ky into Yag minus Yai. Yag is 0.35. Ky is 1.8 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. Nag is 1.8 into 10 to the power minus, after we use these values, Nag will be equal to 1.8 into 10 to the power minus 3 into 0.35 minus 0.232. And we get Nag as 2.12 into 10 to the power minus 4 kilomole per meter square per second. So now let us check whether we get the same value by using equation for the liquid phase. So for the liquid phase, the equation is NaL is equal to Kx into Xai minus Xal. Xai is 0.292, which we obtained just now. And then Xal is given to us, it is 0.15. Kx is 1.48 into 10 to the power minus 3 kilomole per meter square per second per mole fraction. So let us use these values. So NaL will be equal to 1.48 into 10 to the power minus 3 into 0.292 minus 0.15. That gives us NaL as 2.10 into 10 to the power minus 4 kilomole per meter square per second, which is almost equal to the value that was obtained by using equation for the gas phase. So in this way, we get answer for the second question. We have got the value for mass transfer flux. So with this, I will end my discussion on this short video where I have discussed a numerical example where you must have learned how to find out the interfacial concentrations and then how to find the mass transfer flux. Here, an equilibrium relationship was given to us, and we had used that equilibrium relationship for finding the interfacial concentrations. In my next video lecture, I will be discussing another numerical where instead of the equilibrium relationship, equilibrium data is given to us. And there also we will learn how to find out the interfacial concentrations and then the mass transfer flux. For this video, I will end the discussion. I hope you have understood the steps. If you have any doubts, you please mention them in the comment section. So thanks for watching the video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. So as I said, in my next video lecture, I will be discussing one more numerical that is based on finding interfacial concentrations and calculating the mass transfer flux. So hope to see you soon in my next video lecture. For this lecture, have a nice day. Bye bye.